minutes, sir. We can wait for 1 more minute.
Yes, sure.
Okay, we have got about 28 members present over here, including ourselves. So I would like to welcome Dr. Abhimanyu Popli to this faculty development program under the Atal scheme, which is being organized by the Department of Electronics Engineering, AMU Aligarh. And I welcome the participants also on this third day evening session, the online mode. That is the first week, which is going on. Uh, First of all, I would like to introduce the speaker today, Dr. Abhimanyu Popli, who has received his BTech in Telecommunication Engineering from Vellore Institute of Technology in 2006. He received his PhD degree from IIT Delhi in 2018 and is currently working as Senior Research Engineer in Center for Development of Telematics, that is CDOT, in New Delhi. He has more than 15 years of experience in research and development of telecommunication related project of Government of India, and he has worked in diverse field of signal processing, lawful interception technologies, speech processing, and optical communication. All these very relevant to our main theme that we are having over here. He has also architected multi-purpose speech recognition software, and his PhD has resulted into a US patent in the area of keyword spotting in multilingual speech. So his main area of research is actually speech processing and machine learning, and that's what he will be talking about over here. I am sure that the participants in this session will benefit from his vast experience, which actually includes research and industrial experience, which is very, very important. And he will be talking about machine learning as well, so which is a very important aspect of the speech recognition. So we had some discussion about the hidden Markov's model for speech recognition that we saw yesterday. Now you will have a slightly different taste over here, and I hope that you will try to make the maximum benefit from the resource person. Uh, if you are having questions, then you can please post them in the chat box. Usually, the format that we are following over here is that the first session 50 minutes, followed by maybe question answer session or a break, and then another 50 minutes session followed by question and answers. So this is what we usually follow. And apart from this, I would like to thank the Atal scheme that they have actually promised to fund this FDP program, which is in a very important area which involves automation and industrial application thrust area related to speech technologies. So, with this word, I open the floor, and the floor is all yours, Dr. Abhimanyu. Please proceed.
Uh, can you hear me? Can
Yes,
everybody
yes,
hear me?
yes. Fine.
So, first of all, I would like to thank Dr. Wajid for kind introduction. I would also like to thank Department of Electronics, AMU, and Atal scheme. And my organization has kindly given me the permission to share my knowledge, so I'm thankful to them. So, Dr. Wajid gave a formal introduction, my formal introduction, but I would like to start with a small addition to my biography or introduction, that Back in 2010, almost 13 years back, uh, a company came to our office and gave a demo about speaker recognition. So these speech technologies are at that time, that demo and in general the speech technologies like speech recognition and speaker recognition seemed like a magic, because even if uh, I, when we talk about images and computer vision, then you can see something. Here speech, when the computer identifies you as a person or computer identifies the content of your speech, it's almost like a magic, because it's no picture is shown and speech travels through longitudinal waves in the air, and computer then suddenly shows up your identity or your speech content. So at that time, I that motivated me to develop the speaker recognition system from the scratch in MATLAB. At that time, uh, there were no uh, there were no GitHub repositories and things like those. So I developed it from scratch, and that was really enriching experience, and that started my journey towards speech recognition. I'm sorry, I made a mistake. Uh, uh, it seems Professor Omar gave my introduction. So thanks, Omar sir. And
No problem,
yeah,
no problem. It's okay. One and the same thing.
yeah,
Umar Farooq or Dr. Majid, no problem at all.
yeah.
Perfectly fine.
Thank you. So okay, so with this small thing, uh, I'll start my presentation. And so the basic idea is to break that magic into small algorithms, or small mathematical problems which can solve our problem of speech recognition. So I'll also be speaking on speaker recognition. First, I'll speak on speech recognition, and then I will go on to speech or go on to speak on speaker recognition. So speech recognition is a bit longer presentation. So I will take maybe 1 hour or 1 hour 15 minutes on that, and then I will switch to speaker recognition. I hope that is all right. Yeah.
Yeah,
So yeah, and sometimes I can switch in Hindi, because I think everyone here understands Hindi also. Okay. Okay. So speech recognition is basically a sequence to sequence mapping. First slide is that, and then we will go on. I think you have already got an introduction of HMM, so that part would be a bit easier. Then I will switch on to feed-forward neural network, how neural networks came into speech recognition. So this presentation is actually kind of evolution of speech recognition through maybe 2 decades. And so then we will see about how speech recognition is done by RNN, that is recurrent neural network, and where connection is temporal classification comes into picture. And then what are the RNN architectures which are useful for speech recognition, and then a brief introduction to Carly toolkit, and then some recent results. Okay, so let's start with speech recognition. The problem of speech recognition can be thought as mapping of one sequence to another. I was there in Arun Sar's lecture also, and as he explained, speech is transferred in longitudinal waves through the pressure. The parameter is pressure, which travels in the air, and it gets recorded as amplitude in the audio file. So we are basically mapping sequence of values of those amplitudes into characters and then words and like that. So it's basically one mapping. It's a mapping one sequence to another sequence. For example, speech, as you know, can be broken into frames. So 100 frames of speech can be mapped to 3 words like this. So this mapping is ordered and asynchronous. Here I would like to emphasize that all mappings are not ordered and not asynchronous. So ordered, we'll see what do I mean by this. So machine learning frameworks like HMM or neural networks can be used to achieve this kind of mapping. So for example, now coming to ordered and unordered mapping. So I'm showing on screen a very simple language translation. मैं बाजार जा रहा हूँ. I am going to the market can be translated into Hindi as मैं बाजार जा रहा हूँ. Now just notice the position of market. In English, market comes in the last, whereas in Hindi, it comes on the second position. So we see that this mapping is not actually ordered and it is unordered. But in case of speech, it's not like that. The frames which come first are their corresponding characters also come first in the recognition. So this is, we can say, one constraint in or one good thing about speech recognition, that it's ordered mapping, right? And another example is handwriting recognition, which is again a sequence to sequence mapping problem. Here a large number of pixels can be mapped to a few characters. So these are the basic building blocks of speech recognition. So we can see that speech waveform can first be broken into feature vectors, and then comes the decoder part. Decoder consists of 3 blocks, as you can see. Pronunciation dictionary is important, wherein every word is broken into phonemes. Phonemes are fundamental units of sound, like ka, kha, ga. These are fundamental units of sound. These are called phonemes. So cat, for example, is broken into ka, a, t. So here I would like to emphasize that phonemes and alphabets are different. So alphabets may be K, but it consists of 2 phonemes, K and A. So phonemes are the fundamental units of sound and not alphabets. Next comes acoustic model. So acoustic model is used to model the acoustic units, and occupational probabilities and transition probabilities are used to parameterize acoustic model, but we'll see that. And so acoustic model is all about the acoustic units, and language model is all about the text. So probability of any word sequence can be modeled by a language model, and language model also gives you new words. Given a sequence of words, it can predict a new word. So that's how ChatGPT and those are language models, and they are making a lot of impact and revolution. So language model is also required. So first we obtain the probability of the acoustic units, and then language model is applied to get the actual word sequence. We'll see that. Okay, so this is how it works, and finally we get the text output. Now hidden Markov model. So hidden Markov model has 3 parameters, right? So first one is pi, which consists of pi1, pi2 up to pi n. Here n is number of states, and pi is actually which state are you starting with. The probability of starting with a state, that is with a particular state. So that is pi. And then a is transition probabilities. That means you can hop from one state to another with the probability a11. So if you are hopping from state 1 to a different state 2, then the probability which comes into picture is a12. And if you are coming to the same state, then the probability is a11. So like this, you can actually form a matrix with all the combinations of the states that you can hop from one state to another with this probability. And B is what frames of speech you already know. So what is the probability of a frame of speech in a particular state is called is represented as the parameter B. So a fundamental question which I would like to ponder you for maybe 2 seconds is which of these above three parameters pi, A, and B are responsible or useful in representing the stretchability in speech. So stretchability in speech, I'll answer that. So stretchability in speech means that multiple frames can actually represent only one state. Only one state can correspond to multiple frames. When I am speaking cat runs, so a may be spoken in 5 or 6 frames. So this is because the speech signal, especially vowels, are stretchable. So here in this HMM framework, we have a provision for catering to stretchability. For example, consider this probability A22. So if you are in suppose state 2, then you have a finite probability of coming to state 2 again. So when we come again to state 2, that means we can stretch. I mean the speech phonemes can be stretched. So this A is responsible for stretchability, is useful in catering the stretchability. Okay, so HMM speech recognition, as I was saying, so we have to broken this bigger problem or bigger magic into smaller mathematical problems. So there is a very very widely cited tutorial of Rabiner, and every serious researcher in speech technology should refer to that tutorial, and it breaks the problem of speech recognition into 3 fundamental problems. First is likelihood is calculated. Second is here an observation sequence is given and we have to determine the likelihood, which is represented as px by lambda. This is solved by forward algorithm. May I ask, is this HMM thing covered in the previous lecture?
Yes, that was covered, but even if there is a repetition, no issue.
Okay, so I'll go slightly fast on this. Okay, so and the second thing is that if we have a observation sequence X and we already have an HMM, pi A and B, all the parameters are there, then we discover the best hidden state sequence. So most commonly states are phonemes, and so we can discover the sequence of phonemes, or if they are words, we can discover the sequence of words. So let's remember this. The Viterbi algorithm is associated with finding best state sequence or best path. And in the first 2 problems, we were assuming that the HMM is known. So the third problem in HMM is to solve for HMM parameters, which are pi A and B. So these are solved by forward-backward algorithm. I'm not going into details of all the mathematics, but for the timing, we can remember that it is solved by forward-backward problem. So, okay, so in the previous slide, the first step I will show how are we calculating the likelihood. So let's assume that we have a single HMM and each state of that HMM corresponds to 1 phoneme. Okay, so total 40 phonemes are there. In English, total 40 phonemes are there. So we are taking that assumption. So let's consider this word cat. And suppose cat is spoken in 8 feature vectors, x1, x2, like that, x8. Okay, and the phoneme sequence corresponding to cat is k, a, and t. So phonemes are represented. K, for example, I am representing with this symbol, and in between 2 slashes, the phoneme is there. This means that this is a phoneme. So k, a, t. Okay. So now let's define state sequence. Earlier I said that states are same as phonemes for in our assumption. So first 2 frames ka is spoken, next 5 frames a is spoken, and next 2 frames ta is spoken. Total 8 frames. Now we have to calculate the probability of this sequence of 8 frames. So how do we do that? So let's define. Let the probability of transition from a phoneme to the same phoneme means AII, transition from I to I, and to a different phoneme, let it be AIJ. I and J are different, so AIJ. Probability of starting from state QI, let it be pi QI. Let occupational probability of feature vector XT assigned to state QS be this representation. Since it is the probability of XT, so we are giving it as like B of XT. So this is often a distribution like GMM that I'll come to later. But just see, how do we calculate the here I'm just calculating probability of a sequence, the first problem. So so this is equal to, we are starting with pi q1 because we are starting with the first state, and it was ka. Remember, first 2 frames were ka. So starting with ka and then transitioning from first state to itself. So that transition probability was A11. So that's why it is here. And what is the probability that X1 is in state 1? So that's why this is here. And we can see that through this animation, we can see that as we proceed, now the second expression came into picture, and third like this. So as we proceed, there was small blink. That means the transition from second state to second state itself, right? As I told you, the transition probability A22 comes into picture, and from the state 2, now we are switching to state 3, which is t. In cat, the last phoneme is t, so we are switching to that. Like this, it can be this likelihood can be calculated like this. So here now the HMM dominated for the default algorithm of speech recognition, but later deep learning came into picture, which was giving better performance in every machine learning problem. So how do we benefit from deep learning algorithm in this framework? That I'll show in the next slide. So now you can see here that earlier the parameter B, which I told you earlier, the probability of a frame being in a particular state, that is actually modeled as a GMM. GMM is a kind of distribution, Gaussian mixture model, and I will explain that in speaker recognition. But we can assume that GMM is there. So now here, as we saw in the previous slide, that the likelihood was obtained by this product, which included probabilities B, which was modeled by GMM. In place of these GMMs now, we are including this deep neural network. But there's one fundamental problem, that DNN's output probability of phoneme given X, whereas the probability which we earlier modeled was probability of X given the probability of X given the phoneme sequence and the model. So now since DNN is giving us the probability of phoneme given X, so we use Bayes rule is applied here to convert it to the observation probability, the probability of X given the phoneme, like this. So that's how we incorporate DNNs into this HMM framework, and this gives us DNN HMM framework. DNN HMM framework was again popular till maybe 6-7 years back. Okay, so now we have covered the HMM thing, but now next thing is feed forward neural network, and now I will tell you how the feed forward neural network came into picture. So for that, most of you might be knowing feed forward neural network again, but I'll just go through these slides for the sake of completion. Yeah. So what does feed forward neural network do? It is nothing but a function which is mapping, which is used to give us the probability of all the phonemes. Suppose we have a feature vector like this. These green circles are feature vector, and feature vector is generally 40 dimensional or 50 dimensional. So here I have shown only 3 dimensions. So this feature vector, given this feature vector, we have to calculate the probability of all the phonemes. This is the problem we are dealing with. So here we apply a function which is feed forward neural network here to obtain this. Okay, so how is neural network trained? What are the modes of operation of neural network? So there are 2 phases. Like every machine learning algorithm has 2 phases. One is training phase and then inference phase. So posterior probability vector of phonemes is predicted by transformation of feature vectors. That is the prediction mode. So this prediction mode is common in inference phase and training phase. So we try to predict something, and then we see what are the errors. So I would like to give a small analogy here. For example, many of you might be good swimmers or know swimming. So when we are swimming for the first time, we try to move our limbs in random directions. So here also, we first initialize the weights of neural network randomly, and then what do we do in swimming is that we try to guess whether we are going forward or we are drowning. So that is the analogy in neural networks is loss function. So we see that we are going in the right direction or not. So if we are going in the right direction, then the weights are adjusted with lower amount, and if we are drowning, then weights need to be changed by large amounts. So that is the fundamental principle, and here we in neural networks we achieve it by an algorithm called backpropagation. So here predicted values are compared with the targets. We already have targets since this is the training phase. So we already know which phoneme is actually present. So we see that whatever probability, we guessed a probability vector, right? So we see that probability of that vector, how is that value compared with the actual phoneme? If it is high and same phoneme was spoken, then it is all right. But if the probability is low, then an error is calculated. The error would be large and that will be back propagated. So going deeper, this feed forward network for phoneme classification looks like this. Phoneme classification is fundamental, more basic, a deeper problem than speech, a sub problem, I should say, of speech recognition. So we are seeing this green circles, which is the feature vector, and we obtain the probability. The output is y, and z vector here is the actual phoneme, which was, it represents the actual phoneme which was spoken. If this phoneme was spoken, then the probability of this will be 1, and the probability of all the other phonemes will be 0. So this is the target. So now this target is compared with what probability the neural network is giving us, and this comparison is done by Euclidean distance, and basically whatever the error is, that is back propagated to all the weights. Here let's see mathematically how the neural network works. So neural network is basically is this function that first the feature vector is applied to weights, and then activation comes into picture. I'll tell you what the activation is. Then another set of weights, then softmax and another set of activation, and then we get the final result. So these are activation functions. These are some non-linear functions, and these have some important roles to play. So basically, we want to have some non-linear functionality in our network so that neural network can learn non-linear representations in the data. Just see this diagram in the on the right, and suppose these are two classes, blue class and red class. So no linear boundary can be used. Any linear boundary cannot be used to classify to actually make a boundary between these two classes. So that's why a nonlinear function is important in the neural network. And here I would also like to mention that linear prediction and other algorithms have been used, but unless you insert nonlinearity, you won't get the state of the art results which we are seeing these days. So, and another thing is that these activation functions are actually squashing the output, so it does not grow infinitely. So yeah. So and very important property of a very important probability of this activation function is that it should be differentiable, because it allows to backpropagate model's error when training to optimize the weights. So actually, when you minimize any function, you have to differentiate it, right? So all the functions which we saw about neural networks, these weights and everything should be differentiable. So that's why I'm emphasizing that the activation function, although it's non-linear, but it should be differentiable. Only then we can use it. So we can use many kind of loss functions. Earlier I was saying that in case of swimming, you are drowning or not. So if you are, if you are drowning, the loss is more. So here also, in this case, if error is more, then loss is high, and that needs to be back propagated. So many loss functions are used. One famous loss function, one popular loss function which has been used was cross entropy error, and the other loss function is simply the Euclidean distance. So these are both differentiable, and these have been used. Now, I won't go through the derivation of the backpropagation, but simply we can see that how backpropagation works. So as I said, the objective function here is the loss function. So we are taking its derivative with respect to weights, because we have to update the weights. So we are taking derivative with respect to that, because we have to finally find the weights which are giving us the loss. We actually have to minimize the loss. So with this equation, we see that where are we proceeding, and the idea is to minimize the loss. So this differential is used, and this differential, this derivative of O with respect to Wij is computed by chain rule, which we studied in the high school. So chain rule, because it has to be back propagated through all the layers of the weights, and eta here is the learning rate. We want there's a constant which we can set if we want to go fast. Then we can increase it, and vice versa. If we want to go slow, then we can decrease it. So yeah, so this is a multiple choice question, but maybe this you can see in the end. I'll skip that, and let's quickly come to recurrent neural network, because this has been in discussion for sequence to sequence mapping, and this has been a field of research in the past years. So let's see. Now again, this green circle is represented as feature. Then we have some hidden weights, and then the output is y, which we compared with the z. So this was the network till we saw w is the weight and a is the activation function, which I have described earlier. Now here the output is dependent on x only. I mean x through w and a, it is dependent on the feature vector only. But in recurrent neural network, it is not only the output is not only dependent on the present feature vector, but also the previous state. See, the speech, one frame of speech depends on the previous frames also. And if you sometime, I'll give you an exercise. Just if you sometimes open a speech editor and try to listen a very small one frame of speech, then you won't be able to listen anything, because every speech frame depends on multiple previous speech frames and sometimes also the future speech frames. So we have in the previous neural networks, we were not taking that into account. Now we are taking that into account. So the present output is dependent on the present feature vector, and then we will see that when we have to obtain y2, for example, so y2 is dependent on the previous state h1, which in turn was dependent on x1. So basically, the output in recurrent neural network is dependent on the present input as well as the past state. So let's go further. For y3, y3 is dependent on h3 as well as h2. H is hidden state here. H we can call it as hidden state. Okay. Similarly, h4. Similarly, so it goes on like this. Now, doesn't this, I think if you look at this figure, this kind of looks like layers of hidden units. So earlier, we saw that there were two layers of weights. So here, this figure looks like a layer in time. I mean, these can be thought of as layers, although these are hidden states at different times, but these can also be thought of as hidden layers in time. So again, whenever there are layers, we can use backpropagation algorithm, and we can apply chain rule, and we can get the weights weight changes at each time. Okay. So, but as I said that the speech is not dependent on previous frames only. It is also dependent on the future frames also. So now, just look at it here. This is slightly different architecture. This is bidirectional neural network. So y1 is dependent on, or let's see y2. Y2 is dependent on the future states, which are ht, h3. I mean, the output y2 is obtained through this h2 backward and h2 forward and h2 backward. And the input x is also given to this h2 forward and h2 backward both. So basically, here the output is dependent on both previous and future frames through hidden units. Both the hidden units are given as an input to both past and future. So I'm sorry. So y2 is dependent on past and future frames through these hidden units. So let's see, training sequence is presented in a forward and backward manner to two different hidden layers. The output is based on both the hidden layers, the forward layer and the backward layer. Actually, this is the forward layer and this is the backward layer. So in forward layer, the previous input is given, and the backward layer, the future input is given. So this architecture provides both past and future context for every point in speech sequence. Now coming to end-to-end speech recognition. Most of the papers and important discoveries, important innovations are in the end-to-end speech recognition. Earlier, I told you that phonemes are different than alphabets, but we generally recognize alphabets and not phonemes. For example, cat runs, we want the output as CAT, not KAT. That is not readable for a common man who doesn't know linguistics. So we want the output in the form of alphabets. So why don't we map our feature frames directly to these alphabets? So let's see. Feature vectors of speech are directly mapped to characters or alphabet sequences or word sequences in this case. All three models of speech recognition. Earlier, remember I mentioned three models: pronunciation model, acoustic model, and language model. Now all of these are modeled by single or multiple neural networks. There is no requirement for HMM, pronunciation dictionary, and language model. So HMM, which we looked in the previous slides and which was complex, now there is no requirement. Similarly, pronunciation dictionary, which was generally modeled by linguists, not engineers. So that is also now discarded. So neural network will do everything. This black box neural network will do everything. It will make language model, it will create a pronunciation dictionary and acoustic model. Everything will be done by this. And another thing is, for example, earlier in speech recognition, the output of 9 was always represented by NINE, but sometimes when we say 9 AM, we want the output to be digit 9 and not NINE like that. So this end-to-end speech recognition is very intelligent. It will give you the digit 9. It will know where to enter, where to give you digit 9 and where to give you NINE. So when there is 9 AM is there, so 9 AM at that time digit is used. And when we say, for example, in any other textual context, we are using 9, then it will give you NINE. So advantages of this kind of thing is, this kind of neural network is that phoneme dictionary is now discarded. There was a joke which went on in the IBM research labs that whenever a linguist left their team, then the accuracy of speech recognition went up, because linguistic rules are very difficult to formulate, and they are given out by linguists who are not engineers. So now their dependency is removed. So we can say that their linguist job is cut down from speech recognition with this framework. And pronunciations like full stops, commas, apostrophes, these are already there in text, and these can be trained implicitly. Earlier, when we were using acoustic model and all, then there was no, it was difficult to model where you put comma and where, because there is no sound of comma and apostrophe. There are a lot of such silent alphabets, right? So there is no need to convert numerals or dates like this. So okay, so at this point, is there any doubt? I can halt for maybe 2-3 minutes and for any discussion.
Yeah, participants may ask if, yeah. So there is a query in the chat box.
Okay, can you please read?
Okay, can I read it for you?
Yeah.
The first one is how we decide the learning rate.
Yeah, so that is the problem. Learning rate, typically it is of the form of, for example, 10 to the power minus 3 to 10 to the power of minus 7. But again, it depends on the neural network. But general rule of thumb is that as you proceed with the epochs, the learning rate, you keep decreasing the learning rate. So one particular algorithm, I remember that for the first 10 epochs, it kept the learning rate as constant, and then it halved it every next epoch. It halved if the accuracy was decreasing. So based on accuracy also we can based on accuracy, if it is increasing or decreasing, based on if the model is overfitting or not. If the learning rate is very high, we may miss the global minimum. So that fear is there. So if overfitting we detect overfitting. Overfitting, as you know, can be detected when training accuracy is improving, but the validation accuracy is not improving. So then we know that model is overfitting. So in that case, we will. So some empirical algorithms and some rules can be used to adjust this.
Okay, and the question related to the same. One, they're asking, does taking too many epochs also results in overfitting?
Yes. If we take too many epochs, so if we are if suppose we are not getting any improvement after a certain number of epochs, so we can apply some rules. And nowadays these tools have mechanisms to set that if for the loss does not improve over 5 epochs or 10 epochs, then it will stop automatically.
Okay, thank you.
So I think I will proceed with the presentation, and then this was a short break, and then I think I'll take maybe half an hour to complete it, and then we can halt again.
Yeah, sure.
Okay, so now earlier we saw a loss function or error function. So whenever there is a large error, that means we need to adjust the weights more, and so error function was there. But see, loss function of in loss function or error function of feed forward network, the error was based on the output of speech vectors. So for one speech vector, one output will be there and error is there. But speech is a sequence. So as that maturity comes in, or the researchers are actually able to see that the present frames depend on future and past frames also. So the definition of this loss function also changed. Okay, so now the loss function is not based on one feature and one output. Now it is based on a whole likelihood of a sequence. Okay, so the loss is not calculated on each frame. Loss is calculated on whole sequence. For example, cat is running. Okay, so when we input the whole sentence, cat is running, to the neural network, and it will give us a loss. It will not give us a loss at a small frame like ka and a and ta. It will not give loss at every time frame. It will give the loss once we give it a complete utterance. So suppose a training phase of RNN is going on. Okay, and as I said, suppose the whole sequence cat is entered. I'm taking only cat as an example here to make it easier. So cat is entered. Although loss is calculated at the end, but we get probability of phonemes at every time step. For example, this first phoneme, the first frame output is C. First feature vector output is C. Here you can see that actually the output is not phonemes, the output are alphabet. As I said, now we will be modeling the outputs of the alphabet. Okay, So this is the probability of alphabet C, and this is again the C has the maximum probability here. For first 3 frames, C has the maximum probability, and then there is a blank. I'll explain you each of these things. Just one second. Yeah. Okay. So this neural network RNN is giving us the probability vector of alphabets at every frame. Okay. But we will calculate the loss once all these frames, how many frames are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So all these frames have been entered. Then we will calculate the loss. Okay. Now, suppose, see the second diagram, the diagram below. Here, all the maximum scoring alphabet is shown in red. So, in first 3 frames, C had maximum probability, and from frames 5 to 12, A has maximum probability, and in the last 2 frames, in these frames from 5 to 12, A has maximum probability, not A, but the alphabet A has maximum probability, and last 2 frames, the alphabet T has maximum probability. Suppose our output is like this. Now in training phase, we need to calculate the loss. How do we calculate the loss in this case? So now you see that if we have to calculate the loss after the whole utterance is uttered, then if we want, for that we will have to calculate the full likelihood or full probability of the word cat. So cat can be spoken in many ways. Although this is, in this figure I am showing only the maximum values, but suppose C had slightly lower value here and still the cat utterance was spoken. So actually many paths can lead to a single sequence. That's why what I want to show it here. That for example, cat could have been spoken in this way, C, like this. First 5 frames could have been C, and then 2 frames A, and then next frames T, or only 1 frame could have been maximum C and then 5 A's and then T. So actually the problem which I want to point out is here is the significance of this B. What is this B? So B is basically one delimiter, a breaker. So when we give during training, when we give the sequence of alphabets to the neural network, we do not give it as it is. We separate each alphabet by a break character, because speech frames, as you know, multiple frames can correspond to the same alphabet. Same alphabet can have multiple frames. So that's why we have to give a delimiter after every alphabet. So if we call, for example, if instead of cat, if deer was there, okay, so now we always collapse the output of the neural network, and so deer will become DER, because during collapsing what we are doing is multiple frames, we are collapsing it into the multiple outputs, we are collapsing it into a single output. So that's why the blank is included to get the list of all possible target characters. So here the rule is, if the character is repeated, then it can be collapsed. But if a blank comes in between, then it cannot be collapsed. So here is the question that if my bat is, we are calculating the loss for my bat, this sequence, my bat. So which of the paths will give the sequence my bat? So you can see that and guess the answer. So for now, I'll skip on to the next slide. So let Z be the probability of the correct target sequence cat, and let X be a set of 6 feature vectors, X1, X2, X6 like this. Y is, let it be targets of alignment, for example, CAT. So इसमें हम alignment कैसे calculate करेंगे, इसमें हम final likelihood जो है वो किस तरह से calculate करेंगे, तो हम सारे के सारे frames की probability देखेंगे और then product of that, and finally we will sum all the sequences which are resulting into cat, and then we will get the final probability pz by given x, and when we take a negative logarithm of that, that will be actually the loss which we need to minimize. So okay, so I think this might be confusing, so I'll take a couple of minutes more here to explain it. इस पे ट्रेनिंग में हम क्या करते हैं कि हर एक कैरेक्टर के बाद हम एक ब्लैंक सिंबल जो है हम इसमें डाल देते हैं, इंसर्ट कर देते हैं ट्रेनिंग के समय में. दैट इज इंपॉर्टेंट बिकॉज देयर आर मेनी पाथ्स व्हिच लीड टू अ कॉमन सीक्वेंस. So that is the whole idea here. And now as the time is running out, okay, so earlier I said that pronunciation dictionary, acoustic model, language model, everything can be all these architectures can be obtained by RNNs. So here the different architectures are there. Single input is there and single output is there. This is feed forward network. Single input is there and there can be multiple outputs. You give an input and then you do not give any input. Only one input is given, and then we are seeing that this network is generating outputs based on its previous state. So input was only one, but the next output is generated from the previous state, and again next output is generated from the previous state. So आपने input एक ही दिया लेकिन outputs वो generate करता जाएगा. Neural network will go on generating the outputs. So it can write whole poem or whole essay. If you just give it one word, it can go on to write whole essay or whole poem like that. So that is an example of single input and multiple outputs. एक और तरीका है जिसपे we are giving multiple inputs one by one, and the network is generating one single output. So this single output, as you can see, is dependent on multiple previous outputs. So this is kind of an embedding which is useful. So this single output contains information about all the previous inputs. So this is these are some simple architectures. Okay. So how do we here we are in this figure we are generating language model based on RNN. So वो कैसे करेंगे language model? How are we generating? Suppose we have this sentence, what is the problem? So we input X and the neural network is trained to predict is the next output. When we give is, it is trained to predict the next output the. इस तरह से the neural network is always trained to predict the next output. So language model, if you remember the definition of language model, it was the probability of a word given given the sequence of previous words. So that's what the neural network is doing here. It is giving you the output of a problem given the previous words in what is the if you give it is trained to give you the output probability of the next word, which is problem. Okay. So now based on the RNNs, again we can model acoustic model, and like this this pink blocks are acoustic model, and the blue blocks are language model. Language model, I already told you how do we model, by just inputting the next word every time. We train the network to predict the next word. And acoustic model is also like that, we give the first frame, and the neural network is trained to give the probability of the next frame, like this. Okay, so acoustic model is trained, which is shown in the blue, in the pink box, and language model is in the uh, blue blue boxes. Okay, so H1, H2, HT are hidden states, and as you can see, only the last state of the utterance, HT, last hidden state of the utterance, is provided as an input to the language model recurrent neural network. Here, I have mentioned LSTM. LSTM is nothing but a kind of RNN, but a specialized kind of RNN, which I am not covering in this lecture. I'm just covering the basic thing here. Okay, but now in the previous slide, we see that the language model RNN was dependent only on the last embedding. But here we are seeing that the the language model RNN is dependent on all the states H1, H2, HT, H, like that. But these have to be weighted by a weight vector, and this weight vector is called attention. So this is how we are incorporating attention in the neural networks, in the encoder decoder framework. So yeah. So now these we saw acoustic model, language model using RNNs. So these can be arranged in different formats to get a speech recognition system. So these are just some architectures from a Google paper. Since I'm already running out of time, so I'll skip this slide. In this slides, we have just compared these four kind of architectures. These are just arrangements of the RNN blocks, which I discussed in my previous slides. Okay. Here, if we see the results, I'll just make quick observations that baseline unidirectional CDP. CDP means context dependent phonemes. So phoneme-based approach, the phoneme-based approach is still better than the RNN-based approach in most of these cases. So the results are comparative in this. So performance-wise, we are not getting any major enhancements with RNNs. And now we are starting to get something with the more recent networks. But there are many problems with this end-to-end speech recognition. It requires a lot of data. I mean, only Google can have that, or big companies can afford to have that kind of data. For us, for researchers who do not have access to very large amount of data, so our best bet is to train with phoneme-based systems. This is my personal experience. And the other thing is that we in India have so many languages. So, I mean, and we have a very good phoneme rules also. So if you are trying to train your own speech recognition system, then phoneme-based systems might be better. So again, multiple choice question is there. This you may see at your own convenience. And now I'll quickly go to LFMMI and Kaldi Toolkit. So Kaldi Toolkit was developed at Johns Hopkins University, and Dan Povey is the main researcher behind that Kaldi Toolkit. and I've used Kaldi Toolkit, and I think there is a tutorial also in the coming lectures on that. So I think it is still many Python-based frameworks have come in, but still Kaldi Toolkit is very important in its own right, and it is based on time delay neural network that I will explain. That is important. So time delay neural network, it is shift invariant. In this case, time shifted copies of the network are created along time. Again, the fundamental problem is that we want to have information of multiple frames into we want to take into account previous and future frames also. So so we shift the time, make time shifted copies of the neural network, and then error gradient is averaged for all these networks. So all these networks are time shifted copies, and averaged means it is kind of max pooling only, or average pooling. If some of you might be knowing about convolutional neural networks, so there this concept is used. So that's how we are able to get the shift invariance, right? And in speech sequence, this invariance is very important, because you do not have a fixed thing that, for example, when you are releasing, when you are at what time the constriction is there in the vocal tract, and at what time the release takes place, uh, the difference between those two times may vary. So a good system should be shift invariant. Small variance should not affect the output. So that's why this kind of network was used. And as I will tell you, this kind of network has been giving very good accuracies. So this I'll skip first. Yeah. So for example, in this results I'm showing Interspeech 2018 low resource challenge. So here GMM HMM, just see the accuracy of GMM HMM and the accuracy of TDNN. These are word error rates. The lower the word error rate, better is the system. So as you can see, the DNN system or GMM HMM system are far behind TDNN system. So time delay neural network is giving the best output here. So this is what I wanted to show you in this results. And this time delay neural network, so loss function is again like I explained in the RNNs, the loss function is calculated on the basis of a complete sequence. This is the last concept which I want to show you, that suppose you are learning as a students, we are all scholars, so so a fundamental principle in neural science is that if you learn many things and try to do many things at once, then your brain cells neurons improve. So here also, if you want to learn one language, so the architecture is something like this, that you train the neural network on many languages and then you fine tune it for a single language. So multitasking is useful for developing your brain, and similarly it gives better performance in the speech recognition also. Okay. So again, this challenge in 2021 was organized in Interspeech, and again the best architecture was convolutional neural network and TDNN based system, again with Kaldi. So Kaldi is still giving good results and is not outdated. So this one last slide is that you can actually these are different applications. So dictating a letter is one application of speech recognition. See, the theme of this lecture is applications of speech. So human machine speech applications. So speech recognition can be used for dictating a letter, or for home automation, or multiple languages are when languages are expected. So as a researcher, you should think that I have given you some frameworks. I have explained some of the frameworks for speech recognition. Those are just building blocks. For your customized application, you will be needing different blocks out of those. Uh, you will have to choose from those blocks of speech recognition. So for different applications, you can choose uh, uh, different blocks can be chosen for different applications, and uh, you can build your customized solution. um, I think with this I finish off with the first part, which was speech recognition. I'll start with speaker recognition maybe in 5 to 10 minutes. Till that time I can take any questions. Thanks.
Yeah, thank you, sir. So we can see some more questions in the chat window. So let me take. The question is: so can we give a piece of wave that's framed directly as input in RNN?
Okay. Yes. So now, earlier in earlier algorithms, MFCC was used. Always MFCC was used, right? But now, as we have improved, so now mostly spectrogram is used, because MFCC has some some non-linearities and logarithms are there. So, but these non-linearities, logarithms can be obtained. I mean, speech, the neural networks, since it already caters for non-linearities, so it can detect the kind of representations it wants. So we do not need to extract the features. But the problem is, if you are taking raw speech means every second there will be 16,000 samples. So if so many samples are there, so it will become very difficult for you to handle. So these kind of representations, for example, spectrograms or MFCCs, these are all also giving you an abstract representation. Sorry, so that your neural network or the parameters are small. So yes, you can do that, but in that case, your number of parameters will increase. But you can also give one by one, like you can also give samples by one by one as in RNN. So that kind of efforts are going on. So that's why we call it wave to vec, which is the latest speech recognition. So waveforms can also be presented to speech recognition software. Yes. Yeah.
Okay. So next is how to include the delimiters for the continuous speech in CTC.
तो इसमें मान लो एक वी वांट टू गिव कैट द वर्ड कैट, तो इसमें हम क्या करेंगे, डिलिमिटर दैट इज ब्लैंक डिलिमिटर को आई एम कॉलिंग इट ब्लैंक. सो ब्लैंक, देन सी, देन ब्लैंक, देन ए, देन टी, देन ब्लैंक. तो आफ्टर एवरी अल्फाबेट वी आर गिविंग ब्लैंक. सो एक्चुअली अब इसमें यही है, मे बी आई डिड नॉट एक्सप्लेन इट वेरी वेल, but the fundamental, so I'm glad that you asked that. So now when we are training with cat, so अब हमने इस तरह से दिया blank C, blank A, blank T. तो neural network can actually, सच में तो ऐसा नहीं होगा. C will not have just one frame, it can have multiple frames. A can also have multiple frames. सो न्यूरल नेटवर्क जो मैक्सिमम प्रोबेबिलिटीज देगा वो मल्टीपल सीज होंगे, उसमें मल्टीपल एज होंगे, मल्टीपल टीज होंगे, और उसमें ब्लैंक भी होगा कहीं कहीं पे. तो देन वी हैव टू कोलैप्स इट एज आई सेड, एंड देन वी विल गेट द मैक्सिमम लाइक्लीहुड ऑफ द कैट.
So next question is can we TDNN can we use TDNN in sound classification also?
See, any classification problem, I mean, TDNN is a generic framework, and any kind of it can be used for any kind of classification. It is specifically useful for sequences. So sound is obviously a sequence. So yes, it can be used for sound classification also.
Okay. Another one is, are the Kaldi?
Just 1 second. Sound classification is a very, generic term. Speech, phoneme phoneme is also a sound. Phoneme is also a sound. Sound of speaker is also a sound. Sound of a dog or a cat is also a sound. So it is a generic framework for classifying the sounds, whether you want to classify phonemes or different kind of sounds.
Thank you. And one more question is here. Are the Kaldi toolkit and TDNN same, or how they are related?
Kaldi toolkit is a generic toolkit. So in that toolkit, there are multiple recipes. जैसे हम किचन में रेसिपीज यूज करते हैं, उसी तरह से यहाँ पे भी, क्योंकि लैंग्वेज पे we have to select the best frameworks. As previous lecture of Arun sir, in the previous lecture he said, in language things are not very straightforward. So some recipes are there and some scripts are there. So most of those scripts are based on TDNN, but there are some scripts of deep neural network, feed forward neural network also, but mostly it is TDNN and combined with HMM TDNN framework. Most of the scripts are like that. Yeah. So that I think Kaldi का एक पूरा आपके यहाँ session है, तो
maybe that will be the lab session.
हाँ.
So those, I think we have finished with all these questions which was posted in the chat box. Now,
Okay.
if you wish, we can take a break for 3 to 4 minutes, or if you wish, we can continue from here for the second part. It's up to you.
हाँ 3-4 मिनट ब्रेक ले लेते हैं फिर से.
So we can take break for 4-5 minutes. So again, we can continue at 8:20. Is that fine?
Yeah, okay.
Okay. So participant, please be connected. So we'll continue again at
Speaker recognition part will be more interesting maybe.
yeah. So please be online. All the participants, please be online. We'll continue after 3-4 minutes.
Yeah, speaker recognition is a short presentation, not as long as this. So yeah, we can see that.
I have shared the attendance link for the participant. So in the meantime, you can mark your attendance, please.
All the participants, hopefully you would have downloaded the 2 papers that you need to go through, and the group have been formed also with group numbers. So kindly start going through those papers, because ultimately in the next week you need to submit that, and we need to discuss about the content of the paper as well. So kindly download the paper, and the 2 of them are long paper, basic introductory papers. So it will be nice that if you start going through that while the sessions are going on in the online mode, so things will be more clear and you will have better understanding, and you can come up with some of those queries with the expert who are taking these sessions. So I would request to kindly go through the paper as soon as possible and identify your group members, the team, and then you can start interacting with them regarding the report that you have to submit. the template of the report will be available. Dr. Wajid will actually activate that template, which will be again available on the LMS as well. So the link of the paper, again, it has been posted in the chat box. Those who have not downloaded, they can go straight away. And these are the link for template. So Dr. Wajid is very prompt, and he has again done all those needful things. Please go through these things, and these things are mandatory. They carry certain percentage of marks, which will be ultimately evaluated, and the certificates will be given correspondingly based upon the marks that you secure.
So can we start?
Yes, sure. You can start now.
Okay, so speaker recognition, as the name suggests here, the idea is to identify the speaker. So, is there a problem if I speak in Hindi? I think it will be like the interaction will be more.
Yeah, if any participant is having issue,
problem, you can type on chat box if
if you have an issue with it.
anyone has any problem. Okay. Okay, so okay, I'll mix both the languages. Okay, in speaker recognition, we are trying to identify the speakers. So speaker recognition can be of multiple types. Multiple classifications are there, and many applications are there. There are many interesting applications are there. Now आप ये सोचिए कि आपके हाथ में मोबाइल है and आपके फैमिली में कई लोग उसको यूज कर रहे हैं. तो when you say okay Google, so the phone recognizes that who you are and it says welcome so and so. I'm showing you your own routine or your own short schedule. Every family member can have different schedule. So this is one application. One application is, suppose these detective agencies who are intercepting telephones, they have lot of audio files, okay, and they want to recognize that this particular speech was spoken by this particular person. Then you have biometric application is also there. Okay, you have a attendance system and you say a particular word and then it is identified that who is speaking. So these many kind of applications are there. लेकिन जब हम लिटरेचर में स्पीकर आइडेंटिफिकेशन देखते हैं तो स्पीकर आइडेंटिफिकेशन जनरली मीन्स दैट it is just recognizing one speaker. Okay, out of many speakers, it is the system needs to identify one speaker. This is different than speaker verification. Speaker verification में you are claiming that you are such and such person. Whether right and wrong will be detected by system, but you are actually claiming that you are someone. So ये application wise थोड़ा different हो जाता है. फिर उसके बाद speaker independent speaker text independent speech recognition भी होता है, text dependent भी होता है. You have a particular password and you are saying that password every time. So that is text dependent speech recognition. But when some detective agency has a lot of audio files, intercepted audio files, and it is detecting something, then the speaker does not know that it will be intercepted, right? So it will speak, the speaker will speak anything. So that is basically text independent speaker recognition. Right. So, okay. Now, the next classification is closed set and open set. So, one problem is that you are identifying only one of the say in closed set speakers, and the other problem is that any speaker can come. If it belongs to the closed set, it's okay. Otherwise, you can add the signatures of that speaker, and then so you can actually add. So in that sense, the system is not expecting only from one of the closed set. It is, the system is expecting any speaker which may or may not belong to the closed set. So that is open set. So these are the various categories. And again, like we saw in speech recognition, customized solution of speaker recognition can be built once you are familiar with all the building blocks. So here, as I may forget later, some good toolkits are there. One is Sidekit toolkit is there for speaker recognition. Sidekit, SIDE, Sidekit, and another toolkit is Speech Brain, which is being widely used. So these are the toolkits. Okay. So generic flow of speaker recognition, I won't take much time here. Again, framing and pre-processing is done. So pre-processing means pre-emphasis. So those who have attended Arun sir's lecture, he was talking that multiple frequencies, different frequencies, the loudness level of multiple frequencies is perceived differently by human ear. So we actually need to balance out all the bands of the frequencies. So that's where pre-emphasis comes in, that you boost some of the frequencies. So that kind of pre-processing is done after framing, and then feature extraction like MFCC is done, and then speaker modeling. Speaker modeling is essentially the extracting the signatures of all the speakers and storing it into a database. Now, suppose just one second. So now a new speaker comes in. So you will do framing for that speaker, you will do feature extraction, and then you will do speaker matching with all the speakers which you have in database. So signatures of all the earlier speakers are stored here, and you will do the match. You will match the signatures of this unknown speaker with the existing speakers and give out a score. So all the problem of speaker recognition boils down to this diagram. लेकिन अगर हम देखें तो हर एक की स्पीच अलग अलग होती क्यों है? सो उसके लिए हमको ये वाला स्पीच प्रोडक्शन मॉडल देखना पड़ेगा. तो इसमें as we attended research lecture, तो उसमें ये था कि there is an impulse train which is generated by vocal folds, and then there is a vocal tract model. Okay, so impulse train is there and vocal tract is there. So impulse train generates the pitch or a periodic waveform. Periodic spikes are generated by the train generator, and it is shaped by vocal tract model. Everyone has a different pitch. Female pitch is higher than male pitch. So pitch is different for everybody. That is due to everybody has different frequency of vocal folds, and again vocal tract is also different. You might remember that uh, the speech is nothing but resonances which occur in the vocal tract. So if the dimensions of vocal tract are different, so different speech will come out. So that's why all of us sound slightly differently. Then there are some high level features also. Yes, speaking rate is one of the feature, and how if somebody stammers, that is his speech signature. These kind of high level features are also there. Okay. And of course, everybody has a different dimension of teeth, tongue, and length of vocal tracts. These things are different. So in that way, in that sense, speech signal is a biometric signal. Yeah. So we'll come to next slide. So now you have, suppose most of the time when I'm not saying, I will be talking about text independent kind of speaker recognition. Text independent speaker recognition. In the beginning, I showed you multiple classifications. So here I am talking about text independent speaker recognition, where you do not know what text is being spoken. Now coming to evaluation metrics, these are important because how else would you compare two speaker recognition systems? So like in any other pattern recognition or machine learning problem, two types of error are there in speaker recognition also: false negative and false positive. So I think most of you would be aware of this, but still, true positive means अब आपके पास you are offering some of your, for example, consider a speaker verification system. So you are attempting to log on to the system, and you are taking many attempts in order to log on to the system. So speaker will the system will say whether it is correct or it is not correct. It is, so उसको हम यहाँ पर positive और negative कह रहे हैं. System will say whether it is positive or and whether it is negative. But if you have the ground truth, then you will know that whether it is true positive, whether it is the decision of the system is true or the decision of the system is false. So that's what we call true and false. True and false in this matrix. True and false is the first word, and the second word is positive or negative. So positive or negative means whether it is above the threshold, which means that you are permissible, whether it is positive or it is negative. And true and false means whether that decision was correct or not. So coming to true positive rate, it means true positive divided by TP plus FN. If you see it and think it properly, basically this denominator is the original positive samples. So true positives, which were true positive means which was correct and which was the system allowed these speakers. These are positive speakers, and it was true decision. That means it was detected correctly. So that number divided by the total number of speakers which were actually positive. So that is true positive rate. So I won't spend much time on this because this is mostly known. But similarly, false positive rate also has definition. Yeah. Is there some question? Or?
No, there was some interference.
Okay. So in literature, mostly three types of errors are there. Okay. So first is receiver operating characteristics, which is true positive rate divided by true positive rate on x-axis, and false positive rate, which is an error on the x-axis. True positive rate on y-axis and false positive rate on x-axis. So in this case, the system is said to be performing well only if this curve is this knee is towards this point, towards 1 1 0, this point which I'm showing on the diagram, on my slide. So basically what you do is you vary the threshold on the system, and when you vary the threshold, so this TPR and FPR also are varied, and then you get this kind of curve. And the more closer the curve is to this point, we can say 0 1 point, that means true positive, I mean the correct decisions are maximum, true positive is maximum, and this false alarms are minimum. So whenever the threshold is on this point, closer it to the threshold is closer to here, in that case the system is said to be performing the best. So an area under this curve is called AUC, or area under curve. Okay, so the more the area under curve, the better is the system performance. Another kind of graph which we can plot is false reaction rate and false acceptance rate. Again, definition is given here, but what I want to say is that both of these are types of errors. So minimum the error, better the system. So ideally, this curve should be closer to the origin of the graph. यहाँ पे होना चाहिए ये curve, जितना कम हो सकता है उतना होना चाहिए. And this curve is plotted between two kinds of errors. So we have an equal error rate. Equal error rate is point on this graph where two types of errors are equal. So when you see EER in the paper, I think you have to read some papers. So this will be useful there. That EER would be mentioned in the speaker recognition paper. That means both the errors are equal. See, you do not want a speaker recognition system to accept everything, and you also do not want it to have many false alarms. You also do not want it to miss some things. You do not want the system to miss some things, and you also do not want the system to have too many false alarms. So you have to strike a balance, and that balance here is called equal error rate, right? Next, features for speaker recognition. So earlier I discussed that different features can be there. So of course, as I said, that fundamental frequency and format bandwidth, these are different for anybody. So these are acoustic features, they can be generated. And auditory features which are subjective, like loudness, pitch, which are actually perceived by humans. So these are subjective features, but they can also be parameterized into some quantities. So they can be one thing, because if a person is loud, he might be loud always. So these kind of features then are there. Then short-term features are there, and long-term features are there. So in the previous lecture, we learned about narrowband spectrogram and wideband spectrogram. So this is related to that only. Short-term features are 20 to 25 milliseconds, and long-term features are averaged over short time. Averaged over, multiple short-term features are averaged to make a long-term features. Now, long-term features are important because they show us the trajectory of speech, and that trajectory, different people have different kind of trajectories. So long-term features are also important. So again, linguistic features and non-linguistic features are there. Linguistic means phonological features, and non-linguistic features, speaking rate, fluency, as I told earlier. Breathiness, some people have more breathiness. So for that also feature extraction can be done. So here I've mentioned some of the features which are used. So MFCC, linear prediction, in some way or the other, these kind of features actually model the vocal tract. But we also want to include the voicing, the frequency, the fundamental frequency, the pitch, those things also we want to include, right? So that's why we include pitch, energy coefficients. We also append to the features, and then there are delta features. Delta features are used to, again, the time varying, the time variations, time related variations. We want to include them into the include them in our features. Yeah. So those who are researching will find this information useful. These are some of the data sets for speaker recognition. Although there are many data sets, but I have included some of the important data sets. So Vox Celeb database is data set, I should call it. It is used most widely. And then this is our own, I mean, IIT Guwahati has published this data set. So in that sense, you won't find it, you may not find it in the literature, but this can be bought for 10,000 rupees from IIT Guwahati. And this has 451 speakers. And Vox Celeb database is taken from YouTube. So these are the YouTube videos from TEDx. Then there are some NIST data sets are also there. So NIST is, which is National Institutes of Standards and Technology. It is free. It is a paid data set. Most of these data sets have a good cost associated with them, some $10,000, $20,000, something like that. And NIST actually organizes these kind of speaker recognition competitions. So when they organize a new competition, they sometimes they will make the data set available for a price. But these are expensive. So I think those who are looking forward to research in this area, first 3 data sets are low cost or free. You can use them. Okay. अब ये सबसे इंटरेस्टिंग पार्ट यहाँ पर आता है कि स्पीकर मॉडलिंग हम किस तरह से कर सकते हैं. So this is extracting the signature of the speaker. Signature, अगर आपके पास स्पीकर का होगा तो आपके पास कोई अननोन स्पीकर आता है, you can match the signature of that speaker and signature of this speaker. So signature, how do we obtain, or how do we model the speakers? So this left hand side is almost the, I should say, evolution of speaker recognition algorithms, from Gaussian mixture models up to X vectors. So only modeling or signature extraction is not important. We also need some backend techniques. This backend techniques means mostly these are used in matching the 2 speakers. Suppose you have 2 speakers and you want to give a score whether it was the same speaker or not. Then you will use this these distances or these methods. Okay, Gaussian mixture model. Now there is something very interesting I want to show you here. That this is the part A of this diagram. Just look at this. Here, y-axis is the frequency, and frequency means the frequency of occurrence, as in histogram, for example, not the frequency of something spoken. So y-axis is that, and x-axis is, suppose only one dimension of the feature vector you are taking. For example, only pitch, or only 5th dimension, or only the 5th or 6th dimension of the feature vector. That you are plotting, and frequency of repetition of the values of that particular value. So you are getting this curve. So this curve, can it be modeled by a single Gaussian? No, this cannot be modeled by a single Gaussian because it has multiple peaks and multiple valleys are there. So that's why for modeling this kind of distribution, you need Gaussian mixture model, which is, it's a long word, but a heavy word, but Gaussian mixture model just means a mixture of many Gaussians. So if you can see the dotted lines here, there are multiple dotted lines, and the sum of this is Gaussian mixture model. So if you see the peaks of this model, this closely resembles the part A of the graph, because this is also valleys. Here also peaks and valleys are there. So wherever there is a peak, there is a peak in case of Gaussian mixture model also. So what I'm trying to say is that single Gaussian cannot model this distribution, but Gaussian mixture model can model this distribution. Now we use multivariate uh, Gaussian multivariate GMM. That means obviously there are multi-dimensional features are there. The feature vectors have a dimension of 40 or 50. So that's why I'm calling it multivariate distribution. That's why I'm using multivariate distribution to model speakers. So a Gaussian model, which is lambda, I'm calling it lambda. Lambda is parameterized by 3 parameters. The weights, see every Gaussian, think of a single Gaussian. Single Gaussian is parameterized by variance and mean. So if you have one Gaussian, it will have a single mean and a variance. If you have a mixture of Gaussians, then you will have multiple Gaussians, multiple means and multiple variance corresponding to the multiple Gaussians. And each of these mu and sigma will be weighted by a weight by some weights. So if you have capital M number of Gaussians, then you will have capital M number of weights, means and variances. तो उसके डिस्ट्रीब्यूशन हम इस तरह से निकालते हैं कि हम सारे गॉसियंस की जो डिस्ट्रीब्यूशंस है उसको हम सम कर देते हैं एंड देन वी गेट दिस प्रोबेबिलिटी डिस्ट्रीब्यूशन, राइट? ओके, एंड इफ वी वांट टू get the likelihood of the whole sequence of frames, then we will multiply all these individual probabilities. Now the fundamental question is that we have to estimate all these parameters, weights, means and variances. We have to estimate these parameters. So that is done using expectation maximization algorithm. Don't worry, I'll not go deep into mathematics at this point in time. I'll just give an intuition. So first step is expectation. So expectation is calculated on the axis of time. In each of these cases, means, this is mean, this is variance, and this is weight. So each of these quantity is summed over the time axis. See this summation, t is equal to 1 to t is equal to capital T. So a kind of averaging is done to get the expectation of all these 3 parameters, and then comes the maximization step. Maximization is done by calculating posteriori probability of each of the Gaussian component. So here summation is done. This posterior distribution is obtained by summing it along the in the denominator. The sum is done along all the components. So that's how you get posterior probability, and this posterior probability is again used in the determination of the expectation. So this is an iterative algorithm. You first calculate expectation, then maximize it, then again expectation, then again using whatever quantities you have estimated, then using that you will maximize it. So this iteration repeats, and then you get the parameters. Okay. Now with this you can get GMM of every speaker, and whenever a new speaker comes, you can find the probability of that speaker. You can find the probability of that speaker with reference to the models you have created. The lambda of multiple, you have stored the lambda of multiple speakers. Now, whenever a new waveform comes, you can input that waveform, and then you can find the likelihood of that. You can find the likelihood of that utterance with respect to the model. So you will get a score of the speaker. But the fundamental problem is you are lacking. We are lacking some kind of normalization. So for that normalization, universal background model is used. So universal background model is kind of a universal model. That means for all the speakers in the universe or all the speakers in the world, one model is there. And for during enrollment, you can modify that model. You can customize that model according to the speaker. So that in that way, your I would say that your model will be calibrated using a background model, using a universal model. So I won't go into equations. I'll just tell you that, for example, this is the UBM or universal background model, and these red diamonds represent. Suppose these represent the uh, the utterance of new speaker, frames of utterance of the new speaker. Then this shape will be modified to this new shape, and this shape will be modified to this new shape. And since the enrolled speaker did not speak anything of related to this component, so this component is not modified. So basically, this we are adapting the universal model uh, to a new speaker. So now every speaker has a new UBM, which is customized version of universal background model, and score is calculated as the ratio of how likely is the utterance with respect to lambda s, that means speaker dependent model, and how how likely is the utterance with respect to lambda 0, that means the universal speaker independent model. So this ratio, if you take this, this is there. Yeah. So again, next is joint factor analysis and I vectors. So these things are related. This thing, for example, UBM came in 2001 or 2000 or 2001. So, but the later approaches are also related. So that's why I'm telling you all the history. So super vector, you need to understand what is a super vector. A super vector is obtained by concatenating the means of uh, all the components of speaker dependent GMM. So suppose speaker dependent UBM or GMM was there, you can concatenate all the means. So MSH. S means it is dependent on speaker, H means it is dependent on channel. So it is equal to M0. M0 means speaker independent mean. So UBM, the universal model actually. So concatenation of that. So this concatenated version, we call it super vector. So I will just see this second equation, which was disclosed in 2011 by Najeem Dehak, and other authors. In this case, speaker dependent thing is equal to speaker independent supervector plus variabilities. So T is called here total variability matrix, and W is called here I vector. So T is two-dimensional and W is one-dimensional. W is called I vector. T means T is common for all the speakers. So it physically it represents all the variability of the speakers, and W is a weighting factor of this variabilities. So once you have this equation, again you will apply the expectation maximization, and then you will get I vectors, which is W and which is the weighting factor, and this W is called identity vector. Once you get identity vector, you can store all the identity vectors, and when suppose you have to match speaker A and speaker B, you will extract the I vectors by I vector extractor. I vector extractor means UBM and T. If you see this equation, so T matrix is required and UBM is required. Universal background model and total variability matrices are required to extract I vector. Once you have I vector, then you can match it with multiple n number of ways. You can take Euclidean distance of two vectors or cosine distance, but most commonly PLDA is used. So PLD, I'll explain that. But now I will take, I think, 15 more minutes. Is it okay?
Yes, that's fine. That's fine. Maybe 10 to 15 minutes.
Okay. Okay. So, these days every machine learning problem has been broken into deep learning, are solved by deep learning. So here also D vector is used. D vector means D vector is not a particular algorithm or particular architecture, but generic embedding which can be obtained for every speaker. Here in this case, you see that D vector, I mean, first, for every speaker, stacked filter bank is created, and the neural network is trained to obtain to classify or to discriminate against multiple speakers during the training part. So, in training part, your network has learned to to give you whether which speaker had spoken the utterance. Okay, so once the network is trained to do that, now you will remove this layer, because you are generally training with very large number of speakers, maybe 1,000 speakers. So last layer is removed, and now we present a speaker to as the input of the neural network, and speaker will give you an embedding, and these embeddings are used for matching two speakers. So embedding is obtained for every speaker, and for any two speakers, embeddings can be matched with either whatever is there, like cosine distance or Euclidean distance or those algorithms. Again, instead of normal feed-forward neural network, you can use TDNN, which I explained earlier. And this TDNN is this outperformed the I vector which I described earlier. So this is also again in TDNN, one statistics pooling layer is there, and you can obtain these embeddings, and these embeddings can be thought of as signatures of the speakers. This is one concept of linear discriminant analysis which I wanted to explain, because this is very important in the context of speaker recognition. Suppose these three classes are there. These three classes in any general pattern recognition problem, these three classes are there: green, blue, and red. So green, blue, and red you have to classify. So there will be this axis, this particular axis is the best axis for classifying these points. So we have to find such an axis on which, if we project the whole data, the boundaries will become very clear. If you just take the boundaries here, or for example, you take this axis, if you project all these points onto this axis, then you cannot classify the data points. But if you project onto this axis, in that case, you can easily classify the points. So mathematically, what we are doing is, how we find this axis is that we increase the variance. We increase the variance, which is variance between all these classes, and we decrease the variance in intra-class. That means within a class, variance is decreased, and between the class, variance is increased. So when we do this, we get a good axis which can classify all these data points, and that projection is done by this A matrix is that projection matrix. So every I vector W can be projected onto a axis on which the data points are best classified. But for this we need a lot of development data. When you do not have a lot of development data, then you go for probabilistic approach, and that is PLDA, which I told you earlier. So that PLDA is used for matching. So I think only 2 more slides are there. So yeah, so loss calculation for speaker verification. How do you, earlier in speech recognition, I told you, I described several methods for calculating the loss. Now, in this method, how will you calculate loss for speaker verification? That is discussed here. So, see, these things are, speaker verification or face verification, these are similar approaches. So, this triplet loss was used for face recognition originally, and then we tried to fit it in this problem, and it worked very well for this problem also. So in this case, when you train a speaker recognizer, so you enter 3 utterances, not just 1 utterance, but 3 utterances: 1 positive example, 1 negative example, and 1 positive example, 1 negative example, and 1 anchor example. So anchor is a reference utterance. Anchor means anchor is just another utterance from the same speaker. Same means positive utterance. So anchor and positive are spoken by the same speaker, and negative utterance is spoken by a different speaker. So all 3 utterances are given to the speaker recognition neural network, and it learns to classify positive and negative. Here actually the problem which we are dealing with is that we are basically just look at the left part of this figure. Here negative and anchor are near, but when you train the neural network after learning, the negative point will be far from anchor and positive. So this distance has increased, and anchor and positive are spoken from the same utterance, so they are pushed closer. So whatever part we were doing with linear algebra based approaches previously, now we are doing it with this neural networks itself. So loss, this is not difficult. If you see, you will understand that we find the distance between same speakers and difference between pair of speakers. In this way, loss is defined in this way. Okay, so when you take the difference and minimize it, what will happen if you minimize this equation? Then this quantity will become loss. Since L is small, this minus term, this negative term will become large. That means pair of different speaker will have a large difference, and pair of same speakers will have a smaller distance. So that's what we are trying to accomplish. So we minimize this, we formulate this loss and minimize it in neural network. Then since this was ought to be a general applications lecture, so there are several other problems. Suppose you want to identify whether the speech is male speech or female speech automatically. Then also you can use I vectors or same neural networks which have been used for speakers. If you want to classify languages, then also you use same framework. So this framework, these algorithms which I have taught you for speaker recognition have many other applications in language recognition and in gender recognition and speaker recognition. Speaker diarization. So speaker diarization is a problem. Suppose telephone speech is there and 2 people are speaking. So one by one, 2 speakers are speaking. You have to finally give who spoke when. this kind of problem you have to identify, deal with. So in that case, what you will do is you will find I vector for all the frames, and then you will cluster it, and then you will use an iterative algorithm, and then you will get clusters of two speakers, and you will be able to separate those two speakers. So these three applications are also based on speaker recognition algorithms. So and these are some multiple choice questions which may be used. So with this, I end the session, and I think the organizers have my email ID and phone number. So if anybody is having some questions, or later also, of course, I'll answer the question now. And for later also, if you have some questions, we can discuss, or yeah, we can, whatever, we can collaborate or discuss or whatever. So, okay. So, yeah, now I'm open to questions.
Okay. So here, let me take a question from here. Okay. So the question is from Athar Ali: how to decide the mean and variance of multiple Gaussians from histogram in GMM? What is the way? How to decide the mean and variance of multiple Gaussians from histogram in GMM?
Me, histogram I just showed you for histogram just I showed you for to see that how the shape is, how the shape of the histogram is same as the shape of the GMM. But as far as mean and variance, as far as the mathematical problem of estimating means and estimating variance is concerned, there we use expectation maximization algorithm. So this you can you will find many open source tools or toolkits, or you can do it yourself using these equations, expectation maximization equation, where you first find the expectation. Can you? I think, yeah, you can see my screen. So yeah, you can just find the expectation of means and variance, and then find the posterior probability, and then iteratively again go on refining the means and variance, and you will find the means and variance.
Okay, thank you. Next one is they're asking what are the current research areas which is being focused in CDOT?
Yeah, so CDOT is CDOT is a government organization under Department of Telecommunication. So whatever is related to telecommunication is in some way related to CDOT. Presently, we are focusing on quantum communications, and quantum computing is one area. Then optical communication is one area. And some projects are also going on AI ML, and what else? And the other areas, yeah, IoT and machine to machine communication. These are some of the areas. And 5G and 6G are like 4G, 4G, which is being deployed, which BSNL is deploying, is being developed or researched in CDOT. Yeah.
Okay, so next one is can you please suggest what models would be most suitable for carrying out the speaker recognition task? Stage-wise model including front. Including front.
Sorry, I did not get the question.
Yeah, question is somewhat not clear here. And she's asking, can you please suggest what model would be most suitable for carrying out the speaker recognition task?
Yeah, speaker recognition, I think you can try it out with X Vector in the Kaldi toolkit itself. It is giving reasonably well performance, and some deep neural networks are also there in the literature. So earlier I mentioned two toolkits which can be used. Speech Brain is one, and Sidekit is one. So you can try those for developing your own speaker recognition.
So next is what exactly we mean by variability space in I vector.
Yeah, this is good question. Like variability will mean that okay, I'll just show that equation. So variability means suppose you have a model, universal model, but when you adapt it to a one specific utterance, then some variability will come in this that model. So that variability can be due to speaker because it's a different speaker, or it can be due to a different channel, or it can be due to a different session. For example, when I was speaking in speech recognition, then my voice would have been slightly different. Now, since I am speaking from a lot of time, so my voice, I mean, some of the articulators in my mouth might be stressed, so the speech might be different. So each session has some variability, channels have variabilities, and speakers, of course, have variabilities. So that is what is captured in this total variability matrix T. Yeah.
Okay. So next one is, could you please recommend which model would be best suited for carrying out the speaker recognition task with a limited corpus? So she's saying stage-wise, whether stage-wise model, including front-end model, back-end model, end-to-end model.
Okay. So yeah, for all these things, different performances have been reported. But my suggestion would be that you download this. Uh, I'll just 1 second. Mm. So, for example, iVector. I mean, it is best to download the pre-trained models. If you want to do it with iVectors, you should download UBM model and T matrix. If you are using end-to-end speaker recognition, then you can download pre-trained model. I am sure some pre-trained universal models would be available online, and you can adapt with little data what you have. You can adapt it with the Indian database, as I said. One database is published from IIT Guwahati, so you can purchase that and you can do some adaptation with that.
Okay. So is it right to call speaker recognition problem as sound classification problem? Means can we say?
It's a sub.
Yeah.
I think speaker recognition is a sub problem of general sound recognition. But as I said, that multitasking helps in the recognition. So I had seen some papers where sound classification can be. I mean that network is also helpful in speaker recognition, and vice versa. Speaker recognition can be helpful for generic sound recognition. But sound speaker recognition is a sub problem of a wide area of problems of sound recognition.
Okay. So the other one is a basic thing. They are asking what are the opportunities in this domain in India, and what are the essential skills we need for that? They are entry level participant, I think. So they are asking what are the opportunities in India in this domain, and
So
what are the required?
these days, several companies are working in speaker recognition, and I think you have a lecture from Dr. Hemlata tomorrow. So if you go and see on her website, some speaker, they are also doing some work with speaker recognition. So that is one company I can think of. There are several other companies in Bangalore which are also working on speaker recognition. So as I said, there are multiple applications can be there of speaker recognition. It's not just one application. And regarding skill sets, you should be good in linear algebra and deep learning for this speaker recognition or for any other machine learning problem also. But linear algebra is particularly useful for speaker recognition because all these models, variability spaces, and everything, these involve a lot of linear algebra skills.
Yes, I think there are no questions in the chat box now. So I may request Umar sir to please conclude.
Thank you, Dr. Abhimanyu, for this nice lecture, and we had very fruitful interaction with the participants. Also, a lot of queries and questions generated, and this shows that the interest in the participants in the area of speech and speaker recognition.
Thank you, sir. Thanks a lot to all of you and your department for giving me this opportunity. And I hope I'm not from academics, so I hope that I was explained the concepts well. But if several things are left out, please feel free to contact me. And best wishes for all of your endeavors. Thank you.
No, thanks are due to you only, because see, this is not a very good time to have a lecture when you are coming from your work and then you are delivering 2 hours and 3 hours of lecture in between the dinner time, where you are supposed to now take rest, is really taxing for you as well as for the participants also. But the participants, they can sit down and with the mics off and video off, they can relax a bit. But for the resource person, it is really a tough job. So I would like to thank you again for the pain that you have taken and the effort that you have put in. It's not only 3 hours, but you have prepared a lot for this lecture. I hope that we would in near future meet personally, but as a token, we can just offer this virtual memento of thanks and acknowledge your help that you have extended in this FDP program. I'm sure that the participants would have gained a lot, and if they are having any queries, they can pass on to us or pass on to you, and I'm sure that you will be helpful in resolving their doubts and queries.
Thanks a lot, sir. I'm not tired, and it was a very energizing time for me, also re-energizing time. Thanks a lot. Thank you. Good night. Good
Thank
night.
Thank you very much. Thank you very much.
Thank you.
Okay.
Thank you, sir.
Thank you.
Back to Wajid Sahab. Do you want to have any words with the participants?
Yeah, I have shared the link for the attendance. Participant that can mark the link, mark the attendance on the LMS. And if they have not received, I'm just going to share it again on the WhatsApp group. So I just want to thank you all and see you again in the tomorrow's lecture.
Okay, then. Thank you very much.
Okay.
Thank you.
Thank you.
Thank you, everybody. Thanks a lot.